Hi everyone. Today I want to look at another problem in electrostatics. I want to look at a dipole placed in an electric field this time. So we're going to look at a couple different cases. I'm going to start with the simplest, which is just a couple dipoles placed in a constant electric field. We're going to look at the torque on the dipole. We're going to look at the energy associated with rotating a dipole in that field. And in the second case, I want to actually make the field vary in space. Okay, so we're going to place the dipole in an inhomogeneous electric field, and we're going to see what happens to it. So here are a couple cases. Here's dipole number one, here's dipole number two, and now I'm going to place it in an electric field. So here's an electric field, one. Let's just make the field lines uniform. So I'm not telling you what produces the electric field, I'm just telling you there is one in space, and I'm placing dipole number one at an angle with respect to the electric field. And dipole number two, I'm going to place it at a different angle with respect to the electric field. So let's go see what's going to happen to these dipoles. First thing we can look at are the forces acting on the individual charges. Remember, we have a dipole, so that has a positive charge and a negative charge separated by a distance. There will be an electric force acting on the positive charge, and the electric force is in the same direction as the electric field. The electric force acting on the negative charge is going to be in this direction. Right? The electric force is in the opposite direction of the electric field for negative charges. Well, what about this guy? Let's look at dipole number two. Let's look at all the forces acting on dipole number two. We have an electric force acting on the positive side, and we have a force acting on the negative side. So there's a difference between both of these pictures, right? In case number one, you notice that both of these forces are acting in opposite directions, and they're going to tend to make the object rotate. Right? This dipole will rotate in an electric field. How about case number two? Well, case number two, you simply have forces that are tending to stretch the dipole. They don't tend to make the object rotate. Okay, so when we're going to look at this in a little bit more detail in a minute, you're going to see that these forces on a dipole in this orientation will produce a torque on the dipole. Whereas if the dipole is oriented in a direction of the field or opposite of the field, we're going to show that there is no torque. Because these forces don't tend to make the object rotate, where in this case they do. So let's go to the interactive whiteboard and look at a couple specific examples.
Okay, so here we have our dipole again, placed in our field. The positive and negative charges are separated by distance, let's call it d. And what I want to do now is I want to look at the torque produced by each one of these forces. So in order to calculate the torque, well, remember that the force first has a magnitude of the charge times the electric field. Okay, and if we want to look at the torque produced by a constant force, remember what that was? It was the distance to the pivot. Let's put the pivot right at the midpoint. So the distance to the pivot, so that's where the force is being applied, is d over 2. It's the magnitude of the force, which is F, multiplied now times sine of the angle theta. And remember what the angle theta is. In this particular case, the angle theta is defined as this. And that is the torque produced on, or by the force acting on the positive charge. We also have to consider the torque produced by the force down over here on the negative charge. That one's going to have the exact same magnitude. The distance to the pivot is d over 2. The magnitude of the force is the same because we're looking at a dipole, and the charge is the same, and sine of the angle theta. Okay, so we're just about done here. Now we want to look at the net torque. Remember, this here only gives you the magnitude. However, the direction is going to be the same for both of them. Let me add the direction over here. If this force over here on the positive charge is the only force acting on the system, it's going to tend to make it rotate clockwise. How about the negative one? Again, if the force down here is the only force acting on the dipole, it's going to also tend to make it rotate clockwise. That's in the same direction. Therefore, both of those vectors are in the same direction. So the net torque is simply going to be just the sum of both of those. at the end of the day you get 2. And since they have the exact same magnitude, I'll go ahead now and substitute in the magnitude of the force F, which is simply the charge times the magnitude of the field times sine of theta. And that's our net torque acting on the dipole. And I could simplify this a little bit. This 2 will cancel with that one. And let's go ahead and just write our final equation for the torque on the dipole. Can be written as Q d E sine of theta. So that's kind of a useful formula here to remember. You can also take this a step further, and that's typically what people do, is we're going to define a quantity. We're going to define a quantity called the dipole moment. And in this case, it's the electric dipole moment. The electric dipole moment, we give it the letter P. It's actually going to be a vector. And the magnitude of the vector is simply going to be the charge of the dipole, so the charge of either the positive or the negative, multiplied times the distance between the two charges. And the direction, the convention is it points toward the positive charge. Oops. Points toward positive charge. Okay, so in this figure here, if I'm going to plot what this vector P looks like, the vector P basically points in this direction here. That is our dipole moment associated with that dipole. And the reason we're going to want to define the dipole moment is because the torque now, you can actually write it as a vector equation. The torque as a vector can be written very simply as our dipole moment vector cross product with the electric field. Okay. So there you have it. That is the same equation as the one I wrote up here. Remember how you expand a cross product is you take the magnitude of one vector, you multiply it by the magnitude of the other vector, and then you multiply it by sine of the angle between the two vectors. So in this specific case, let me draw the vectors on the side here. So we have our dipole moment vector, which is like this. It has a vector P, which has a magnitude of the charge times the distance between the two. Our vector E is in this direction. That's the direction of the electric field. And the angle theta that goes into our torque equation is the angle between the dipole moment vector and the electric field vector. Okay. So in this direction here ends up being perpendicular to the dipole moment vector and the electric field vector. If things are in the plane like this, usually you can pick a direction for the torque as being either clockwise or counterclockwise. And that's kind of what I've done up here. Okay, so there you have it, folks. There's the torque of produced by an electric field on a dipole. So it depends on the angle, right? We have our general equation here, which is P sine of theta. So we have a couple specific cases to look at. For example, when is the torque a maximum value? Well, for any given dipole, which has a dipole moment P, the maximum angle or the maximum torque will be produced when sine of theta equals to 1. Right? When we have sine of theta equals to 1, that's going to produce the maximum torque for any given electric field and dipole. And we get that when the dipole moment P is perpendicular to the electric field, because in that case our angle theta is actually 90 degrees. Okay? And the torque is simply going to be the dipole moment times the electric field times sine of 90, which is 1. So that's it. The magnitude of the torque is simply this. If you want to write it now in terms of the charge, remember you can simply do that with the charge times the distance between the positive and negative charge times the electric field. And that's the magnitude of the torque. Okay, so let's compare the two cases I had on the board now. So we have dipole 1, which is located in a constant electric field. However, it makes an angle of 30 degrees with respect to the electric field. Whereas in case number 2, you have the dipole that's in the same direction as the electric field. And in both cases, we want to look at the torque acting on the dipole. Again, we can look at each individual charge, look at the forces. However, I want to use the formula we had in the previous case, which said that the torque is P cross E for both cases. And remember how that vector P was defined. That was our dipole moment. The vector P was the charge Q times the distance between the two charges. And the direction was from the negative to the positive. Okay, so negative to positive. Okay, so let's draw the vectors P and E for both of these cases, for dipole 1 and dipole number 2. So here's what we have for dipole number 1. Here's the vector P. Here's our electric field. And I've said that the angle here was 30 degrees. All right, compare that to case number 2. Case number 2, again, our dipole moment vector goes from negative to positive. So in that case, it's the same magnitude, however, the orientation is different. That's the direction of P, and the direction of E is also in this direction. So in this case, the angle between them is equal to 0 degrees. So if we apply our torque equation and we want to find how big the torque is, so let's just look at the magnitude of the torque. The magnitude of the torque will simply be P E times sine of 30 degrees. So that's Q times the distance between the positive and negative charge times the magnitude of the field, and sine of 30 degrees. Okay. So one last step, QD E divided by 2. All right, compare that to this case. The net torque acting on dipole number 2 is simply going to be P's the same, E's the same. However, we have sine of 0 degrees. And sine of 0 degrees is 0. Therefore, the net torque acting on dipole number 2 is 0. Whereas the net torque for dipole number 1 is definitely non-zero. So what we're going to have here is, in this case, we're going to get some rotation of the dipole. In this case, no rotation. Okay, now I'm going to look at the potential energy of a dipole in a field. Again, I'm going to use this definition of our electric dipole moment, which is a vector that pointed from the negative charge to the positive charge. And we can write the potential energy of a dipole in a constant electric field in terms of the electric field, this dipole moment, as P dot E. This is a scalar product. So if you want to write that in terms of the angle between both of those vectors, and just in terms of the magnitudes, simply minus PE times cos of theta. So that's kind of an important equation. So again, the energy can range over a whole series of values, because the angle theta, I can place this dipole at any orientation with respect to the electric field. You can look at when the potential energy is a maximum. So when would we have a maximum value for this potential energy? Well, we'd have a maximum value whenever the angle theta is equal to 180 degrees. Right? When the angle theta is equal to 180 degrees, cos of 180 is minus 1. So the energy of the dipole in the field is PE. As you get minus PE times cos of 180, which is minus 1, which cancels with the original 1. We get a minimum value of the potential energy when the angle theta equal to 0. In that case, that's when the dipole moment is aligned with the electric field. In that case, you have a minimum potential energy. And the energy of the dipole in this case is minus PE. Okay, there's a case where the potential energy is equal to 0. Right? The potential energy equals to 0 when the angle is 90 degrees. In that case, so 0 is when our angle theta equals 90 degrees. The potential energy of the dipole is equal to 0. Okay, the actual values of potential energy aren't really that interesting. What's more interesting is when you change, right? When we change the energy, or when we try to rotate the dipole, we might be asked how much work is needed to rotate a dipole in an electric field. We know there's forces that the field produces on the charge. So if I wanted to rotate, I have to do work on the system. So let's look at this specific case here down at the bottom that I've sketched out. So I have an initial dipole where the dipole moment is aligned in the same direction as my electric field shown in red. And in the final position, I simply want to rotate this dipole by 180 degrees by some mechanism. I'm not really showing you, but I'm just giving you the initial and the final steps, what the orientation of the dipole looks like in the field. And we want to calculate how much energy is stored in the system, or how much work did you have to do to accomplish this. So, to calculate how much work you needed to do, you simply have to look at the work needed is basically just the change in potential energy. If you're not sure about this, think about just the mass. Right? If I just have a mass on the ground and I want to lift it up all the way up to here and lift it up through some height. If I want to know how much energy is required to do this, all you have to do is simply compare the potential energy at the top versus the bottom. Okay? In this case, you usually set the potential energy equal to 0 at the bottom, and the potential energy in the final step is simply mgh. So the amount of energy required to raise this mass a certain distance h is simply equal to mgh. You look at the change of potential energy in the system. That's exactly what we're going to do here for the dipole, except the potential energy is not simply given by the mass times the gravity times the height above the ground. Okay. The potential energy for a dipole in a field is given by our other expression here, which is negative the dipole moment times the electric field times cos of the angle between both of those vectors. So the work needed is the change in potential energy. That's a final potential energy minus an initial potential energy. Now those are going to be different from each other because the angle is different in each case. So you got to be a little bit careful. So our final value is simply, well, how did we start? We started, so our final value is shown down here, and that's the case where the angle is 180 between the dipole moment and the electric field. I've actually calculated that one right here. That was the value of the potential energy of the dipole in the field. So it's simply PE minus, what's the initial value? In the initial configuration, the dipole moment is aligned in the same direction of the field. That is when the angle is 0 degrees. I've shown that one here. And the potential energy is negative PE. So when you include everything together, the work needed is simply going to be 2 times the magnitude of the dipole moment times the magnitude of the electric field. Okay. And that is going to be a quantity that's going to have units of joules. Corresponds to the amount of energy that's required in order to accomplish this. Okay. Notice we're going to get a positive number. We're going to get a positive number because we have to do work against the electric field in order to rotate this object. It's not going to rotate by itself. Okay, you have to put energy into the system, and this is how much energy you need to put in order to rotate this dipole. Okay, now I want to look at what happens when the electric field is not constant and compare it to the constant case over here. Now let's just look at the torque. The torque for case number 1, where the dipole moment is aligned in the same direction of the field, we just saw that the net torque was equal to 0. We had forces acting to the right on the positive charge, force acting to the left on the negative charge, and those forces didn't produce any rotation. For the case down or illustrated in the bottom figure, if the field was constant, again, we had forces acting at a certain distance from the pivot, and those forces produced a torque, right? They would tend to make the object rotate clockwise. Clockwise rotation. The magnitude of the torque was given by our dipole moment, the magnitude of the electric field times sine of the angle between them. If you substituted in our value for the dipole moment, or the magnitude of the dipole moment, which is simply Q times D sine of theta. So that's the torque. One thing I didn't mention before, however, it's very, very important. Let me write this down. Is the forces for case number 2, even for case number 1, the forces balance out, actually. So although they do produce a torque for case number 2, the net force acting on the dipole is equal to 0, right? Because the charge is the same, the electric field is the same. These forces are in equal and opposite directions. They produce a torque, however, they don't produce an acceleration of the dipole. You'll simply rotate it. Okay? You're not going to move the dipole. You're not going to lead to any translational motion of the dipole. And that's kind of the big important point, and the biggest difference here between the case where the electric field is constant versus when the electric field varies in space. So let's have a look at it. Okay, so now let's compare the case where the electric field is not uniform in space. For that, I'm going to look at the field produced by a negative charge, and I'm going to place the dipole with its dipole moment aligned, pointing toward the negative charge and making some angle, as shown in the bottom figure over here. So let's look at the forces acting on the dipole. Well, you're going to have an attractive force between the positive part of the dipole and the negative charge. So that's going to be a force pointing to the right. And you're also going to have a repulsive force. I'll draw it in a different shade here, because these two negatives will repel each other. So you're going to have another force pointing to the left this time. Let's call that F2 and call our first one F1. Now, one thing that is different from the case of the constant electric field is that both of the vectors for the constant field, both of the force vectors had the same magnitude. In this case, F1 in magnitude is going to be bigger than F2. Okay. Therefore, there's going to be a net force acting on it. The net force is not equal to 0, like in this case. Okay. This net force acting on the dipole was equal to 0. So that means, well, the dipole is going to be attracted to the negative charge. Okay. If there's a net force, there's going to be an acceleration. Okay. How about the torque? Well, even in this case here, there is no torque. Okay. Although there's a net force acting on it, the torque acting on the dipole is going to be 0. And you can see that just by looking at the figure. All of these forces do is the forces tend to make the object stretch. Right? They're acting in opposite directions, but there's no rotation. Okay? No rotation. All right. Now take the case now where our dipole moment is again at some angle with respect to the axis joining the negative charge producing another electric field. In this particular case, again, we can look at the forces acting on the dipole. And the forces, well, you're going to have an attractive force acting this way. And you're going to have, again, a repulsive force acting away from it. Now, these vectors have a different directions, number one. So you're still going to have a net force acting on them. Both of these vectors will never cancel out to give you 0 net force because they're in different directions. So we're going to have a net force not equal to 0. In addition, you're going to have a net torque. You can calculate the torque by looking at each individual component and repeating the steps we did for the regular dipole in a constant field. You can place a pivot here at the center of the dipole and look at the total torque produced by each force and then add them up as vectors. So we'd have to do the torque produced by the force F1 as a vector plus the torque produced by the force F2 as a vector. Each one of these cases I can use my equation. I can use it's the distance to the pivot, it's the magnitude of the force, and times sine of the angle between them. Okay, you'd have to do a little bit more algebra, but the key point is that you can have a net force in this case, and you can also have a net torque. Okay, this is to actually calculate the magnitude is a little bit more complicated. However, the concepts should be clear just by looking at the force diagrams. Okay, so just to summarize the key points, we defined a new vector today called the dipole moment. The dipole moment, we gave it the letter P, and the magnitude anyway was the charge Q of the dipole multiplied times the distance between the two charges, and the direction was from the negative toward the positive charge of the dipole. This was particularly useful because you can then use the definition of the dipole moment to look at the torque acting on a dipole, and the torque is simply written as P cross E, and if you write that in terms of the magnitude of the torque, you simply have the magnitude of the vector P, the magnitude of our electric field, and there's also that angular dependence that was really important, because there's some orientations of the dipole in a field where there is no torque acting on it. For example, if it's parallel or anti-parallel. The other important point was that the net force of a dipole in a constant electric field is 0. E is constant. Okay. Because you have equal and opposite forces, they don't produce a net force acting on the dipole. We also discussed potential energy, and we looked at a case where the dipole was placed in a constant electric field, and for that case the potential energy of the dipole is simply minus P dot E. If you expand that scalar product, you simply have PE cos of theta. Now, the actual individual values of the potential energy are really not that interesting. What's more interesting is when you change the potential energy of a dipole. So you either have to do work or electric field does work. Does work on the dipole. So we looked at one specific case where we rotated the dipole and looked at how much energy is required in order to accomplish that rotation. The last thing I looked at, we looked at placing a dipole in a field that was inhomogeneous, so it wasn't constant. And what we found in that case, you could still have a torque depending on the orientation of the dipole moment with the electric field. And the major difference between that and the constant electric field was now the net force is non-zero. Okay. So the dipole will not only tend to rotate, but it will also tend to accelerate. Okay, that's it for today, folks. Thanks for watching. If you have any questions, just leave some comments.
PhysicsNinja.org